the addition rule, using the addition rule for probability problems. And today we're going to add in what's called the multiplication rule. Oh, sorry, this says Unit 10, but that was last year. It's Unit 9. Cool. And we're going to need to define two different types of events, independent and dependent events. There's a multiplication rule to use for either of these types of events. And then we're also going to put together and just review what we did last week with mutually exclusive and non-mutually exclusive and these new ones. So I want to review from last week, mutually exclusive, non-mutually exclusive, and then that way we can compare those to these new types, independent and dependence, and put them all together so we'll know better which case we're in and which like rule or formula we need to use to solve our question. Okay. Oh, I left my notes out at the table. Rats. I think we'll be fine. Let's try it without my notes. Suppose we have a bag of marbles with 3 blue marbles and 1 red marble. So altogether, there's 4 in the bag. We do a 2-part, 2-stage experiment. We reach in the bag and randomly pick out 1 marble, put it back, and reach in and pick out a second. The question to solve: find the probability that the first pick is blue and the second pick is red. So see how we're looking for 2 different events to happen. First pick is blue, second is red. So this is a 2-part or 2-stage probability question because there's 2 different events here. Event A is finding the probability that you reach in and get a blue. And then event B, reaching in second time and getting a red. So I want to model this with a tree diagram to see all of our total outcomes. So let me go ahead and change my color so it doesn't get too confusing here. So with blue, there's 3 blue marbles in the bag, right? So stage 1, we reach in, and what are our total outcomes that we could get? We could get 1 of the 3 blue marbles. So I'm just going to write B for blue. And then there's that 4th marble, which is red. Stage 2, we reach in and pick a second time. So we reach in, and it says that we are putting back the first one, right? So we reach in and get a marble, we put it back, and then we reach in and get a second. So the outcomes for this second stage should be the exact same outcomes as stage 1. So for stage 2, I could get blue, 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 and then red. I'm going to fill in the reds afterwards. Blue, 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 and red. Blue, 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 and red. And then last up, I could get blue, 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 and red here as well. I'm going to put my reds in there. Okay. So there's our tree diagram for this scenario. And we're asked to find the probability that you reach in and first get blue, and second time we reach in, we get red. So how many different branches or roots on our tree diagram match up with that scenario? Let's count those up. I'm going to color this green to identify the ones that would be a success, the outcomes that would give us a success in this scenario. So first pick is blue, second is red, first pick is blue, second is red, and then here we see blue and red again. And we wouldn't use the last part of our tree, would we? Because that's getting a red first, and that doesn't count as a success for us. So there's three successful outcomes. How many total outcomes are there? What's our sample space for this experiment? Remember, the sample space is the total number of outcomes you see at the last stage, the final stage. So how many total outcomes are there on this final stage? Can we count those up? Can any of you tell me? Sorry, let me rephrase my question. Can any of you tell me how many total outcomes there are here? Picking these two marbles.
4.
There's 4 if we just pick one time, right? Because there's 4 colors or 4 different marbles. So you're right. For the first stage, it's 4, but we're doing this twice. So then we look at the final stage down here. In this case, there's only 2 stages. The final stage tells us how many total outcomes there are, what our sample space is. So how many different like entries do you see along that final row?
I'm sorry, can you repeat what you said? You cut out.
I'm cutting out. Okay, thanks for telling me.
You're so welcome.
Can you hear me right now, Manaya?
I can.
So, sample space is all the outcomes, all possible outcomes. The final row, if you make a tree diagram, tells you the sample space or shows you the sample space. Every one of these outcomes on the bottom row, so blue, that's one outcome, that's blue, blue. Another blue, blue, that's 2 outcomes. This is 3 outcomes, this is 4. So if we add up all these entries on the bottom, that's telling us how big our sample space is, how many total outcomes.
16.
There we go. Thank you, Manaya. 16 total. And thank you, Manaya, for speaking up and working with me on that.
You're so welcome.
High five, dude. So there's 16 total. We've identified 3, the ones I circled, that count as a win or a success because we got a blue, then a red specifically. So this probability of picking blue and red, or specifically blue then red, is 3 out of 16. We can't reduce that fraction, so we'll just keep it as 3/16. What's the percentage? 3 divided by 16? 18.8%. Now, I want to show you something with the separate probabilities. Manaya first said there's 4 outcomes, and she's right. There's 4 total marbles in the bag, right? So let's look at these separately of picking a blue and picking a red. So on the left side of my screen, I've got those up now. So probability of first picking blue. So if we kind of back up, we've already solved this question, right? We've found it's 3 out of 16, 18%. But if we back up and examine those like separate probabilities, first just picking a blue, what would that be? Successes, there's 3 blues total out of 4 total marbles in the bag. If we're just focused on picking a blue. And then below that, probability of picking a red. So what is just the probability of reaching in one time and getting that red? 1 out of 4, because there's 1 red and there's 4 total outcomes. Look what happens with these two individual probabilities and how they relate to the 3 over 16. 3 over 4 times 1 over 4 gives us 3/16. 3 times 1 on top, 4 times 4 in the denominator. So it appears that if we know the separate probabilities, we can multiply them together to get that total 2-stage probability. Now, why is this different than what we saw last week with mutually exclusive or non-mutually exclusive? The difference is in the question. This is asking us, look above in the center of the screen with me right here, find the probability. The question is, or the task is telling us to find the probability of blue and red. Blue and. That word and is our key word. Last week, with our mutually exclusives and non-mutually exclusives and our addition rule, the word that we're looking for is or. So event A or B, that's the addition rule. If you see a question like this, where it's 2 steps or two outcomes we're interested in, but the word is and, we're looking for this to happen and that to happen, then we're multiplying our separate probabilities. Like we see here, 3/4 times 1/4 is 3/16. There's a lot going on so far. That's it for this screen. But can I, before we move on, I want to hear back from you guys. So tell me in the chat or with your mic, or I guess you could turn on your camera and give me a thumbs up or a thumbs down or a thumb sideways. Tell me where you're at so far. Can I hear from all 4 of you guys, please?
I think I'm good.
You good so far? Thank you, Manaya. Andrew, appreciate that feedback. Antonio, if you did a thumbs up on the screen, I missed it. How you doing? Thank you, Antonio. Aaron, how are you feeling so far?
I'm feeling okay.
Okay. All right, thanks for the feedback, folks. So now I want to ask the same question, except we're going to make one change in the question. We were told on this screen to do this experiment, get a blue, then a red, and in the middle, we had to put it back. We put back our blue marble. So what happens if we change that and we say don't replace it? Now we want to do the experiment again with one change. We do not replace that first marble. So here's a reminder in my box. The bag started with 3 blue and 1 red. Before we do the probability here on the left, I want to map it out again. And if it's okay with you guys, I'm going to not do the different colors just for time. So stage 1. We reach in and there's 4 marbles, blue, 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 red. Stage 2, assuming we get our blue marble first, what's left in that bag? That's going to change what's available as outcomes for that second pick. So I'm assuming now for stage 2 that I've removed 1 blue marble. So what's in the bag? What's available? Blue, blue, red. See how we're cutting out we're assuming, we're hoping we get that first blue. So for step 2, there's a blue, and there's a red, a blue, and a red, and then a blue, blue, red. Let's identify the ones that meet our goal, meet our criteria. So I first reach in and get that blue, and then I get a red, blue, then red. And of course, the fourth branch on our tree doesn't count because it's picking a red first. So we're disregarding it just like last time. But what else has changed this time? The sample space is different. There's not 16 entries on the bottom. See that? There's going to be just 12 entries on the bottom. So let's write this out the way we've been doing it. Probability of blue and red in that order is 3 out of 12. And this we can reduce. That's 1 out of 4. Yes, 1 out of 4, which is 25%. Let's examine both individual probabilities like we did last time. Oops, hang on. So I should have maybe erased this. I don't think I like this. So I'm going to cross this out. So probability of reaching in and getting that blue on the first pick. That is still 3 out of 4 because there's 3 blues available on the first pick, right? And there's 4 total. How about the getting a red after we kept the blue from the first pick? We did not replace it. I'm going to say red, not replacing blue. Okay, so here's our second pick. Well, there's 1 red available and 2 blues available, right? So that's 1 out of 3. And now if we multiply these, separates, we get 3 on top and 12 on the bottom, which is the same thing we got by doing our tree diagram, which comes out to 25%. So what's different here is that when we don't replace that blue marble, it affected and changed what was available for that second pick. So in this case, when we don't replace our first marble, the second pick is dependent on what happens in the first pick. The second event is dependent on the first event. This time, the second event depended on the first event. We're still multiplying the two probabilities together, but it's not the same second probability, is it? Instead of being, what did we have last time? 1 out of 4, it's 1 out of 3. So we had to account for the fact that we removed it, and that totally changed our sample space, and it changed our available outcomes. I'll keep this on the screen if anyone's still writing. And then I want to basically define both of the types of events we just saw, and we'll formalize the formulas for each case. The first event we did back here, this is an example of independent events because we replaced that blue marble. So the second event was completely fresh and brand new, and it didn't matter what happened the first time. It didn't matter what we picked out of the bag of marbles. They were independent of each other. When we don't replace the first marble, the second one does depend. So this is an example of two dependent events. One depended on the other. So let's put all this together. Independent events versus dependent events. Here we go. So independent events do not depend on each other, and there's no or there is replacement. So if we're dealing with marbles and taking one thing out of a collection of others and not putting it back, or yes, putting it back so that every stage is brand new and fresh, then these are independent events. So let's say this: two events that do not depend on each other. And I'm going to add in, yes, replacement. We replaced the marble, and that made the two events completely fresh. The second pick didn't matter for the first pick. Has replacement. Yes, there's replacement. In our formula or a shortcut we can use for independent events, if we're to find the probability of event A and event B happening, then it's the two separate probabilities multiplied together. Probability of A times the probability of B. But if we have a case where one event does depend on the other, then those are dependent events. So below, two events that do depend on each other. No replacing. So in a case like the marbles, we kept the marble. We did not replace it. Our formula, probability of event A and event B, is the probability of the first event, same as before, times this, probability of B given that A has already occurred. I'm going to change my color and write that part out below it. This symbol we're looking at, B line A, this means probability of B given that A has already occurred. So in our example, that's multiplying by picking a red after we've taken out a blue already. I'm going to wait a few moments for people to write. And then I want to make a table with you of just extra notes of comparing last week's with this week's, comparing the addition rule to the multiplication rule. And what's the difference and how do we know when to use which rule? Because really we have 4 different formulas now. We've got our 2 for mutually or non-mutually exclusive, and then we've got our independent or dependent events. And really each one is different. So let's compare those together now. And then we'll try some practice problems. So for our probability problems or questions, here's the 2 basic outlines. On the left, probability of A or B, or keyword. Both of these are addition rule. And then today's are on the right, probability of A and B. So this is 2 events that both have to happen. Last week was one or the other, or. So these use one of our multiplication rules. So let's go back to the left again. Probability of A or B, addition rules. We had 2 different versions, mutually exclusive or non-mutually exclusive. So the first one, and this is not new, this is just from last week. So mutually exclusive. This means A and B, event A and event B, they cannot happen at the same time. They are exclusive. They are VIPs. So they don't occur together. A and B cannot happen simultaneously. Big word, simultaneously. They can't happen at the same time. Cannot happen at the same time. And so this is like having our deck of cards and we need to draw a red or a black. And you can't have a card that's red and black at the same time, right? So mutually exclusive, we simply add the 2 separate probabilities. So probability of getting a red or a black card, probability of A or B is the 2 separates added together. But then we also learned about non-mutually exclusive, meaning the case we're looking for can happen at the same time. Non-mutually exclusive. A and B can happen simultaneously. And when this is happening, this is like picking a 2 or a red from our deck of cards, right? And there is a card that is the red, the 2 of hearts or the 2 of diamonds. So you've basically got these 2 different ways that a card can be a 2 and a red at the same time. So for this, probability of A or B, we're adding the 2 separates and subtracting out the overlap. Probability of A plus probability of B minus any of those cases where there's overlap. A and B together. So that's just some review from last week and when we use those cases. How do we start to know? In your question, we have to identify, is it saying event A or B, or is it A and B? So this is today's new information on the right. So independent events. Does the outcome of one event matter for the one that came prior? If they don't affect each other, I'll say A and B don't affect each other. Then we simply multiply the two single probabilities together. And then also there's dependent events where one is dependent on the first, where the second stage depends on what happened in the first stage. A and B do depend on each other or affect each other. Let me change that. Affect each other. This is like taking a marble out of the bag, reaching in a second time, and taking a second marble without replacement. Then our formula is probability of getting event A and event B. It's the probability of the first event, easy to figure out, times the probability of the second, given that A has already occurred. So there's last week's addition rules plus today's multiplication rules, and then some ideas on when we use which. First, start by asking yourself, are they asking me for an either or? Because then we're on the left using addition rules, and we have to figure out which one. Are they asking me for event A and B to happen? First, I get this and I get that. Then I'm using the formulas on the right for multiplication. And we have to still figure out which one is it. Are we in an independent or a dependent scenario? I'll keep this up on the screen for a few moments if people are writing. I misspelled independent. Independent. It's funny. So for today's mastery test, everything will be in a multiplication rule question. Everything will be either independent or dependent. I thought it would be good though, since today's formulas are kind of similar to last week's, and the questions might sound similar too. That's why I wanted to go over both of these now, all four formulas, so we had them together and compared and contrasted, so we know how to start our questions. But just know that today's mastery test is going to be all of the stuff in red, independent or dependent. So I wanted to practice some problems like those with you. So our first step is always deciding, is this independent, where second stage doesn't matter about the first stage, or is it dependent, where the first stage affects the second stage? And that'll help us figure out how to proceed. Okay, so just like last week, these questions are kind of wordy. So don't spend your time, please, at home right now, writing out the whole word problem. I'd rather you took a picture of it so you're not writing for like 10 minutes. Sarah picks out 7 different colored crayons that match the colors of the rainbow and places them in a box. She asks her brother to randomly pick 2 crayons from the box, one after the other. The probability that the first color is violet and the second is orange. There's our 2 events, event A and B. If the first crayon is replaced. So they're telling us in this question we're going to pick 2 crayons and we're going to replace the first one. So we pick 1 out of those 7 and then put it back. And then we pick another 1 out of those 7 and put it back. And we're hoping we get violet and orange. So, and then there's a second question below. Here's our second question, but we'll do that afterwards. So for our first question in the middle, what are the total outcomes? It says that there's 7 crayons and they're all the colors of the rainbow. So just to be clear what those are, what's in this bag that we're randomly pulling out one of, what could those be? There's red, Roy G. Biv. That's how I remember the colors of the rainbow. So red, orange, yellow, green, blue, indigo. I guess that's what that is. And then violet. There's our 7 different outcomes. So I reach in and I pick one of those 7 different crayons, and I'm hoping I get violet, the V. And then I reach in and there's still 7 because we replaced the violet. So what's the first probability here? Probability of getting violet and orange. So there's our actual question written out with symbols. Probability of violet and orange. Well, probability of violet. And then we're going to multiply that to probability of orange. So what is the probability of just reaching in and getting violet? We're picking 1 and we're hoping to get violet. How many successes are there? How many total are there? Anybody, please. Just the probability of violet. How many violets are in the bag or in the box?
1,
Yes. And how many total crayons are there?
7.
7. So we're dealing with 1 over 7 for violet. Okay, then we assume we get it. Then we put it back. What's the probability we get an orange?
1,
Out of?
7.
Exactly. Is that Delaney?
Yeah.
Good job, Delaney. Thank you for jumping in there. Hope the rest of you are still with me. So we're just figuring out those 2 separates, multiplying them together for 1 over 49. If we map this out with a tree diagram, then we'd basically be saying, here's our first stage: red, orange, yellow, green, blue, indigo, violet. And then underneath all that needs to be all 7 again. Red, orange, yellow, green, blue, indigo, violet, right? That 7 exists under each one of the original 7. That's where the 49 is coming from. There's 49 different total outcomes. So that's where that 49 is emerging from. So here's our answer. The probability of violet and orange with replacement is 1 out of 49. 1 out of 49. Now below that, I've got the same question, but it says first crayon is not replaced. So our second question here, probability that the first color is violet and the second is orange if the first crayon is not replaced. So violet and there's our key word. So that's a hint telling us, okay, I know I'm doing an and problem, so I need to be using my multiplication rules. And it says not replaced. So that's a clue that we're doing dependent events. The second event depends on what happens the first time. It's going to change our sample space. So this is probability of a violet, not violent, violet, times the probability of getting orange, assuming given that violet has already been picked. Given violet has happened. So the probability of violet is still 1 out of 7 because there's 7 totals, 1 violet. Now, I want to get an orange. How many oranges are there? 1. But how many total crayons are there if I take the violet out? 6. So instead of 1 over 7 times 1 over 7, we end up with 1 over 7 times 1 over 6. Much different than last time. So that's still a 1 chance out of 42. 7 times 6. Now, if we map this out, we're going to show the first stage. Roy G. Biv. Okay, there's our stage 1. And underneath needs to be all the 6 leftover options after we took out the violet. So I'm not going to show the whole thing because it's too much to put on our paper and screens. But this would be everything but the violet for the second stage. So Roy G. B.I. See how there's just 6 left over that it could be. Roy G. B.I. And this is where the 42 is coming from. If we tallied all these up underneath see, I don't have space for this. No one does. But this will add up to 42 if we wanted to see all those outcomes on paper. Now, part of the reason we're using these formulas is so we don't have to do the tree diagram every time. Sometimes it's going to be ridiculous and impossible to make a tree diagram. Like this case, I mean, we'd have to show all these and it takes so much space. So this is why I want you to use tree diagrams for simpler problems so that you can see where the numbers are coming from. But we need to be able to rely on our formulas and not have to make a picture each time because it's not practical to do it each time. Awesome. Antonio, thank you. I see you figured out that sample space for the second question. Folks, before we do any other questions or new problems to solve, any questions about this example, please?
I'm sorry, the 6 was for what? From what?
Good question. The 6. Where did this 1 out of 6 come from? And why is it 6 and not 7? Because let me erase this here. So in our box, here's the box. And inside the box are these 7 crayons, right? Red, orange, yellow, green, blue, indigo, and violet. So there's our 7 crayons. And there's 7. We want to find that second pick. First we pick a violet. So I remove the violet. This one here has been taken out. And so now when I go to get my second event and my second pick, what's inside that box? Red, orange, yellow, green, blue, and indigo. Violet's gone now, right? So what's our sample space for that second pick? It's just 6. There's 6 outcomes. We're hoping for orange. But any of these colors, they're all just 1. So it doesn't really matter what that color we're looking for is. The odds of getting any specific color on the second pick or second event is only 6. And that's why this is not 7 for the second time. On the first pick, sorry, I'm supposed to say first. On the first pick, there's 7 in the box. But on the second pick, we kept or did not replace our violet, so there's only 6. The violet is pulled out the first time and not replaced.
Okay.
Does that help, Aaron, or not yet?
It makes more sense now.
Okay, thank you for asking. And the key word is in the writing, in the words, it's first crayon is not replaced. Because we didn't replace it, it changed that second pick. That second event depends on the first. And that's why it's 1/6. Any other questions or concerns? Okay, let's look at some more. I took our questions from Edmentum. I changed the numbers though. So they'll look familiar when you do your test later. You're throwing darts at a dartboard. I should have put a picture of a dartboard up. Usually there's a bullseye in the center. It's like the hardest spot to hit with your dart right here. And then there's like bigger circles going out of it that are worth like less points. So you get more points if you can hit your dart smack in the middle at the bullseye. And then you get a little less here and a little less going outwards. You're throwing darts at a dartboard. You have a 1/8 chance of striking the bullseye each time you throw. If you throw 3 times, what is the probability you will strike the bullseye all 3 times? So we're looking for a probability of 3 times in a row, bullseye and bullseye and bullseye, getting it right in the middle each time. And notice that this is not just 2 things happening. Technically, this is 3 events. Event A, B, and C. And it's saying, I want to throw my dart and hit it right in the middle in the bullseye 3 times in a row. Oh, nice. Someone's got a chat. 1 out of 3. Let's see. Okay. You're on the right track, but how would that, let's see, I'm trying to think of how best to answer you. Okay, Antonio, hold that thought. I don't have a terrific answer for you yet. I don't think it's going to be that. We know that it's a 1/8 chance of striking the bullseye for each time. So for a moment, pretend that we're just throwing the dart once. Okay. This is asking about 3 times in the row, but for a moment, let's just assume we're just trying to figure out, well, what is it for one bullseye? It's telling us in the problem, it's 1/8 chance. We don't know about the other outcomes, right? They're not telling us anything useful about the other rings, only the very center, the bullseye. So for just getting a single bullseye, it's a 1/8 chance. Now, if I want to do that 3 times in a row, then that's going to be throwing it and throwing another and throwing another. Now, it's not saying anything about replacing or not replacing, right? We were hoping it would, because that would tell us if it's dependent or independent. If we assume that putting a dart on the board, like here's my first dart. Let's say I throw it and I get it, bing, right there in the bullseye. Assuming that it doesn't affect when I throw the next one and the next one and the next one. It doesn't say anything about it affecting it. So if I'm going to throw 3 darts, then each bullseye is a 1/8 chance, and it's not affecting the previous, or the previous throws are not affecting the future throws. I'm going to assume that because it doesn't say anything about it. And there's no reason to think that it should affect it. So the probability of getting 3 bullseyes in a row above here in my 3 events is 1/8 times 1/8 times 1/8. So you're on the right track, Antonio, and thank you for jumping in and responding. We're going to use the fact that we're doing it 3 times like you did, but we have to multiply each separate probability together 3 times. So we put all this together. 1 times 1 times 1 is still just a 1, but 8 times 8 times 8 is something much bigger. 512. 8 times 8 times 8. So the problem didn't mention anything about replacing or not replacing, and it also didn't mention subsequent throws, second throw, third throw, fourth throw being like hindered or changed by our previous throws. Because well, I don't know why, because it just didn't. So because it didn't mention that, then we can assume that this is an independent scenario. Because it doesn't matter what happens the first time, we still have a 1 1/8 chance of striking a bullseye. Maybe the key word is above each time. Each time, meaning the subsequent times, the second and third throws don't matter, don't change coming from the first throw. So maybe there's our key word. Each time it's 1 out of 8. So that's our clue that this was an independent case. Also, notice that the question isn't saying anything like getting in the bullseye or in the next ring. There's no or here. So that's our clue that it's not a mutually exclusive or non-mutually exclusive problem. It's an independent or dependent problem. So look for those keywords. Just so you know, all these questions are going to be independent and dependent multiplication problems. Okay. Oh my God. It's almost time to go. Let's do another one. And I noticed that there's actually quite a few in Edmentum like this too. So read through this with me. You are performing 2 chemistry experiments. The probability that both experiments are successful is 22%. If the first experiment is successful, the probability that the second is also successful is 31%. So this is a little confusing how they're stating this. But in the middle, if the first is successful, the probability that the second is also successful is 31. What this is telling us is probability of, it's like saying the second one is successful 31% if the first one is, given that the first one is. So this keyword here, if the first one is successful, that's like saying given the first one is successful. So that's like saying the probability of the second experiment, given that the first experiment was successful, is 31%. And the very beginning is telling us the probability that both experiments are successful. So I think what they're saying is the experiments probability separately. So probability of first, that is 22%. And separately on its own, probability of second experiment is also 22%. But then they tell us, oh, if the second one has a probability of 31%, given that, or if the first one is already, that's different. It's 31. So because of this middle of the problem, the second sentence here, this is our clue that it is a dependent scenario because of this phrasing. If the first one is successful, the probability that the second is this much, 31. So this is a dependent scenario, and we know how to deal with dependence. Probability of A and B is the probability of A times the probability of B given A. And we have both of those numbers. Oh, this is asking us the probability that the first experiment is successful. Well, that's weird. Okay, so let's answer 2 questions quick. So probability of just first experiment, well, they're telling us that at the beginning. the probability that both are successful is 22. And the second, on its own, is 22. But to find both of them successful, we're going to use that second one they give us, 22% times 31. And we have to multiply these as decimals. So we turn it into a decimal, 0.22 times 0.31 to find whatever that is. Zero point 0.0682. So that's 6.8%. Okay. This went by way faster than I thought. So I'm going to let you guys go. Have a great day. Try the new mastery test called multiplication rule for probability. That's your homework for today, and I'll see you tomorrow.
All right, bye.
Bye.
Josiah.
Bye, everybody. Bye, Manaya. Bye, Aaron.